take a poster and stretch over wood blocks.
Okay, this
Where do you
is
get the wood?
It looks like a t-shirt, right? And they just wrapped it around.
Right here.
Someone
Oh.
by the cone
Okay.
or lumberyards.
All right, so
I got
here's what we
one
have.
that's on my back.
Okay, we're going to talk about two topics today. Number one, it's the first section of chapter 2, which I know we've been doing chapter 2, you know, like the sections we're doing, like section 1.6, 1.7, 1.8. But this is actually like the first number that actually says 2.1. We're talking about slope and rate of change. This topic is something we've already discussed, but we've never really tied everything together. Because obviously, if you think back to your days in Algebra 2, pre-calc, and Algebra 1, in fact, there's a lot of things that they always talk about slope, right? Slope. It's called the rate of change. It is actually an average rate of change.
2 credits or is that? No, it's just.
Average rate of change. The slope formula that you've had since Algebra 1 is this one. y1 minus y2
X.
x1 minus x2.
Two.
It doesn't matter, it's as long as you have coordinates.
Oh, no.
The coordinates you have are, x1, y1, x2, y2. Just you have two coordinates. You subtracted them. That's an average slope. Now here's the idea.
Are you closing them?
I just don't want to get hit in the head. All right. This is what they call an average rate of change. What it is it's basically looking at, if you were looking at two dots, right, and you're picking the line that goes right through. I'll just pick these two, so it looks better. All right, that's an average rate of change. Now, why would we ever do something like that? Obviously, with lines, drawing linear graphs, but if you're like plotting data for a business, data is messy, right? It's not going to be perfectly linear. You hope that it is. You can kind of predict what's going to happen later. But if you know your data's going up and down, slope can change, right? This slope, if things we've talked about in the past, this is a positive slope, right? Why slope is important? Slope tells us the direction it's going. This graph is increasing because the slope is increasing. It's a positive slope. It's going up to the right. Now, why would you ever do something like this? If you had a curve, so your data is just like all over the place, you kind of plotted it over the last couple months, your data is kind of all over, and this is kind of what your data is starting to look like, right? The idea is that slope changed over your business model a few times, and what an average rate of change is that you're picking two dots on the curve, any two dots you want. The trick is to pick them as close as possible. I'm going to pick two dots that are close as possible, and the idea is that this is an average rate of change. You're looking at just the average slope to see is that graph increasing or decreasing over that time. Why they say push them as close as possible? Because if you start to drag this dot, and you put that dot over here, you'd obviously see a negative slope, and it doesn't represent that, right? It was actually positive for a little while, then it switches to negative, then it might go back to positive for a while, it might switch to negative. It's switching constantly. And the idea is that this gives you an average. This is that idea where you're taking a limit and you're going as close to that limit as possible. You're squeezing between two numbers to get as close to the number as possible. That number you're trying to get to, that perfect slope, like at this very moment, the exact slope right there, that is called an instantaneous rate of change. Instantaneous rate of change. I don't think I spelled it right.
In what situation would you need it?
In an instant, Luke.
You forgot the other T.
Instantaneous.
Instantaneous.
I don't know if
Yeah,
it's
yeah.
spelled
So we're
right.
not-
That says instant. Shut it.
Like
Let's
this?
see.
He needs another and.
Where's,
I didn't-
oh wait, I need that search bar. Where's that?
Instantane. You need another A in it.
Ah,
So what example, like,
Tis.
That says instant.
Instantaneous. That's how I
why are
spell
we
it
finding
too.
the slope on this curve?
I didn't even look up there. Luke, if you need it in an instant,
instantaneous. Okay, I forgot an A.
We just
There we go.
Instantaneous,
I know I
right?
can't spell this in my life. All right, here we go. All right, instantaneous. There we go. Okay.
Perfect.
All right, instantaneous rate of change is the exact slope at any particular moment on a curve. Now, why they would ever have to do this? The easiest example I've provided you in the past was this idea of civil engineer. Civil engineers work on road and public types of construction projects. What a civil engineer would do, probably for instantaneous slope, is they would rate a curve for a certain speed. So, so the idea is that if you're going around,
It's like going into a curve, dude.
yeah. So like the idea is like if you're going north of Garner here past Quick Start or Quick Trip,
Going to
and it has that little curve that goes out by the golf course.
go like
It
this.
does something a little more drastic than this. At one point, there's a street sign. So here's Quick Trip.
Quick Start.
With a K.
And to the right,
Yeah, it's with a K.
GLS.
KWIK.
There you go. All right, Quick Start. There it is. There's a sign that says 35 for that curve. The idea is that some civil engineers figured out on that curve at any moment the instantaneous rate of change safely to traverse it, to go from one edge of the curve to the other edge of the curve. The rate of change should be 35. They made that curve in such a way that the slope is a constant 35 for the most part, at its peak bend, right? And the idea is that what we know in math is that slope changes, right? As we go from here to here, the slope is actually changing, to go. So the idea is that they're giving you what they have is they found, the instantaneous rate of change, probably the peak speed limit on the curve. And so they're saying it's rated for 35 safely. You could go faster than that, but the idea is that they're trying to tell you like the peak is 35, you should slow down, because at some point the curve does change. You will have to slow down to make sure that you can get over the entire bend. It doesn't mean that you're going to go to like a negative speed limit, but the slope is changing, and they're giving you some instant number for it. Now, why we have instantaneous rate of change? The idea behind it. It's used to find any particular number for your data for some project where it's changing over time, and you want to know exactly when it's starting to change and what it's going to go to, and you can use it as predictors, right? If the curve's stuck on its current trajectory, where would it actually be going? So, like for instance, they do this in case of NASA. Let's use NASA as an example. They have something flying out in space. It's going through an elliptical curve. They're tracking a bunch of asteroids in space, and the idea is that what they're looking for is their trajectory. They're always looking at the slope where that thing is heading. Because if it were to suddenly break off, maybe there's some gravitational force that pulls it away from its present curve. Okay, like the moon. That's a good example.
Like the moon.
Where would that asteroid actually be heading then?
Towards the moon.
Something would change, right? That the gravitational force is now going to pull it away from its current trajectory, and now it's going to change course. Now they do this over the entire lifespan of the asteroid. They're constantly tracking what they call near-Earth objects, where they constantly have to put in consideration when that asteroid gets nearer to the sun, other planetary bodies are going to affect it, and where's the new trajectory going to go? Because it's changing over its entire life. It's getting closer to the sun, or it might shoot out further because maybe it got closer to Jupiter, and Jupiter affected its gravitational pull. And so they're constantly reevaluating, and they always have predictions like, okay, this asteroid that passed by Earth, 2 months ago, in the year 2030, it's going to be back because of its elliptical path. Now, where is it going to be? Is it going to be closer? Is it going to be further away? What planetary bodies were influencing it at the time? And they predict when it's going to be close, and then they do the real calculations when it's starting to come back.
Why don't they just look?
It's pretty impressive stuff because they're tracking it. For us, we're looking at a 2D image, but they're tracking it because they're using the actual elliptical path and the actual rate of changes of those planetary bodies that it's passing by. They're doing some really interesting stuff with it, and they can predict when the next one would come.
You
Now,
should
obviously,
be-
there's
you should
new
be
ones
one
all
of
the
them.
time, but they're doing. This is serious
Yeah,
math.
I bet
They're
you
doing it.
Calculating,
You don't
so-
think you can do it?
Okay,
Sean?
no, got it.
Oh, I think.
All right.
Okay.
2 questions.
Okay.
How fast would you go around that curve?
At a peak,
Just casually.
casually, if
How
it's
fast
rated for 35,
Yeah.
I don't know, 35, 40. I'm probably not going to push it past that. It depends on the weather condition, right? If it's raining, I'm going to go slower. If it's snowing or
What's
icy.
gonna
If
happen
it's
if
sunny
you, what's
outside.
gonna happen if you
Sunny,
go
30
faster?
or 40.
What's gonna happen? If
on that.
it's actually 30, it's not 35.
30, okay.
And I've gone 45 on it and I've been fine.
And,
I feel like I'm leaning
I've
a
gone
little
Question
bit.
number 2,
Yeah.
going
Like, I
to
feel like-
the
The idea is
I'm feeling
inertia's
good.
starting to pull you a little bit.
Yeah, but I'm still fine.
Now the
You're
reason
not
why
in a
they
minivan.
the reason why they also rate that is because of it's a generic vehicle. It's how you stay on the curve, right? And they also want to put in consideration if you were to have a sudden flat tire, right? In that situation where you're laning and you're going too fast.
Pop.
What if you pop a tire?
You're
That would be
dead.
so much fun.
That would be that's the ultimate risk, right?
Yeah.
So they give you a speed. It's usually slower because they want you to be able to stay safely on the curve. That's the idea. Now, obviously, the number it's different because every vehicle's different. They're doing it for generic weight,
I'm not
a
happy.
generic
I'm not
vehicle
happy with
itself, but it gives you an idea of what you could do. Right? Question.
Oh, my second question.
Second question. Go.
Are those glasses real glasses? Or
Yes, they are.
Did you get from Claire's? They have fake glasses there.
You're old, you're
I
in
really
for that long.
you can try them on.
Where'd you get them? I want to try them on.
Well, I'll try one.
You just said we could try them on.
We'll do that. All right. Now,
Swearing.
hey, here's the idea. Let's walk through the idea of what we're doing here. I want to give you an example, just so you can see kind of the concept that can be involved here. Okay. All right. I'm just going to give you a curve here, and I'm going to give you a formula that goes with it. This is our one example today, and then we're done. One example.
Finish.
Then we're finished. Okay, so here we go. The formula I want to give you, let's go with f of x equals, let's go with x squared plus 4x plus 4. This is my equation. And that curve is it's going to hit positive 4. It's going to be going up, that type of thing. And it's a parabola, that's how I know it. It would, if I graph that thing, and I factor it apart, x plus 2, x plus 2. So it potentially has 2 x-intercepts. It has the same x-intercept twice, right? These are the x-intercepts. So it's actually -2 squared. So that means it's actually bouncing off of -2. So my graph's a little bit off. It should be -2 here. And it's doing that. That's what it's actually doing. And again, how I'm doing this. If I factor, it tells me x-intercept. Since it was the same x-intercept twice, it bounced off of that, and I know the curve's going up. So this is actually the lowest point on that curve. I actually figured out the zenith. I don't need to do anything fancier with that. Now, why I'm giving you this. If I want to know any specific slope on that curve, let's say that's a curve we're going around a bend, going north of Garner here. And the idea is I want to know the slope at any particular moment, like this moment right here. Let's say I want to know the slope right here at what is that, -4. I want to know that slope. Now, we can predict what it looks like, right? It looks something like this. Agreed?
Yeah.
Like the slope is going down.
Yeah.
So the trick is, if you really want to know what that slope is, like the average, pick 2 numbers that are close to it. Okay, so we can use this formula over here. You pick 2 numbers that are close to it. Let's say these 2. You pick those 2, you find the slope, and that's roughly the same number. Okay, it's close, right? That's the idea. And so those coordinates, now what the coordinates I'm picking, let's say I picked -3 and I picked -5. And I'm picking those dots right there and there. Now I want to go as close as possible. I might want to pick decimals. But I'm picking 2 numbers. Those are my x numbers. So -3 and -5. And I want to know the y coordinates. And then I want to figure out the average slope at that moment. Right, the average slope. So, -3, if I plug -3 here, this will spit up my y number at that exact moment. I can kind of look at the graph and kind of see what it is. But -3 squared, that's 9. -12, if I plug in -3 in there, so that's -3 plus 1, or plus 4 is 1. So far I'm at -3, comma 1, so I'm a little bit lower than I showed. -5, if I plug that in, -5 is 25 minus 20, that's 5, plus 4, that's 9. So 5, comma 9. So it's way up. I'm not, mine is drawing is not drawing a scale by any means, as you can tell.
It's pretty low.
And the idea is that now that I have my 2 coordinates, I can go find slope at that moment. It's gonna be a negative slope. You're subtracting the 2 y numbers, right? This is the average rate of change. So 9 minus the 1, -5 minus the -3. So y numbers on the top, x numbers on the bottom. This turns out to be a -8 over these turns out to be a -2. So it actually ended up being what? That was a positive 8, sorry. Positive 8 over negative 2, which is negative 4 over 1. So it's dropping 4 running 1 each time. That kind of looks like what that slope is. Does that make sense?
Yes.
You pick two dots that are close to it, you can find the average rate. But here's the thing. That's an average. That slope wasn't great. You're actually seeing it. I picked 2 coordinates. Mine wasn't even drawn to scale. But I picked 2 dots, and I was drawing the lines connecting the 2 dots. That was not even the exact slope at that moment. It was close. My predicted slope was this one. It was leaning in a different direction. The reason why. You want to be as close as possible with these coordinates to get a more accurate reading of slope. Slope could be a little bit more tilted, it could be leveling back out. To do that, that's what an instantaneous rate of change is, not an average. How we find instantaneous. This is our last bit of note here. Instantaneous rate of change. This is that thing we've been talking about. Instantaneous rate of change. We have a formula for that. Instantaneous rate of change is this one. The limit as h approaches 0. So as I get closer and closer to that exact point where I want to find the slope, this is the formula we use. What does that look like to you?
Over H,
That looks
not over
right.
That
X.
looks like a differential quotient to
Doesn't
me.
it have to
That's-
be, isn't it
that's why
supposed to
we
be
do it.
over H, not over X?
Over h. So,
Oh,
over h.
All right, you're probably the
So-
smartest person I've ever met.
So here's the
My
idea.
whole life.
Why we do it? Why we do a differential quotient? It is literally a formula to find slope when you're getting your h's, your coordinates for x, as close as possible where they're nearly on top of each other, and there's no difference between the coordinate you're trying to find slope at. That's the idea. I'm pushing the x's as close as possible where there's literally no gap between them, and that'll get my slope to the exact moment. Now, if you do the differential quotient for this problem, that's where this thing will give you an actual number, where we're plugging in zeros and everything. It will give you a formula, and then I can go find the instant slope at that moment. So, to do this, here we go. This is my last problem of the day. X plus h squared, and this is the limit as h approaches 0. X plus h squared plus 4x plus h plus 4
Actually, never won.
minus the original function
Wasn't Friday.
all over h. That's the formula we have, right? We go through all the math. Now, we figured out earlier my slope is about -4, roughly. But this will give me my actual slope. So if I do all the math here, this turns out to be x squared plus 2xh's plus h squared plus 4x plus 4h plus 4 minus, I'm going to subtract all this stuff, that's x squared minus 4x minus 4. That's all over h, limit as h approaches 0. Yeah, terrible h. As h approaches 0. If we did this right, my little shortcut that I told you, you know you're doing it right, the things without h's go away. And we're left with only things with h's on them. And then we're supposed to divide everything by h, and then eventually plug in 0 for h's, because I want to get h as close to 0 as possible. And what this will give me is it will give me the slope at that exact moment. And it will give me a formula. So, if I do this, if I divide everything by h, here's what I get. Right, you agree that's everything divided by h?
Yes.
Now, I want, if there's any h's left over, plug 0 in for them, if you can. Well, we can. We can plug in 0. That's how we evaluate limits. What you're looking at here, that is the formula for slope on the curve at any moment. Now, why that's important? My goal was to find the slope
At any moment.
at this exact point. So we can just plug in the number now. So this function gave me slope. It's slope on the curve at any moment. So if I wanted to find the slope at exactly -4 on the x-axis, all right? I don't care what this other y number was at that moment on that curve. I just want to know what slope was at this moment. All you have to do is take that slope formula, which is my 2x plus 4, plug this number into it, and this will give me my slope.
Look what I said, Sam.
Wow.
So the two coordinates I picked was a great predictor of it. It was actually giving me the exact slope at that exact moment. The average and instantaneous are usually close, but you can have differences by a few decimal places depending on how close to the x's you get. Does that make sense what we just did there? Tomorrow, we're gonna go more in depth in this. It gets way more challenging.
How?
Way more
I'm
challenging.
excited to start tomorrow.
Love
I
me
want
a
the
shower.
shortcuts, it's easy.
Yeah, with shortcuts, yeah, this is definitely something we're gonna want to learn with
Shortcuts,
shortcuts for.
So you're gonna use
Hard
shortcut
to utilize it.
So,
I'm not.
Can I have a spot, please?
You're not what?
Not allowed.